Welcome to the Bodhi Academy. My name is Amcha Classo, and in today's video we'll start with a new chapter, chapter 3, class 12, chemical kinetics. Now when we talk about chemical kinetics, so if we have say a simple example to begin with, say we are talking about food getting spoiled. So now when we say that the food is getting spoiled, we can say that it is a visible process that is occurring, as in it is possible for it to occur. Now what are the factors that are leading to this spoiling of the food is unknown to us. Then secondly, how fast is that whatever bacteria that is acting upon the food, how fast is it going to act so that the food gets spoiled. These things also we don't know. So when we have similar examples where we talk about the rate or the speed of any process or reaction that occurs, we are talking about chemical kinetics. If we look in terms of thermodynamics, we have learned only that we can tell if the reaction is feasible, as in is it going to occur or not. But when we talk about if a reaction is going to occur, then how fast will it occur or how slow will it occur. So in that case, then what are the factors that will affect the speed of it. These all things we are going to learn in this chapter of chemical kinetics. So the word kinetic itself is derived from the meaning known as the moment. So now in this chapter we will be dealing with average and instantaneous rate of reaction and the factors affecting this. Some elementary ideas about the collision theory of reaction rates are also given. However, in order to understand all this, let us first learn about the reaction rate. So now we will see what do you mean by rate of a chemical reaction. So some reactions such as ionic reactions occur very fast. For example, precipitation of silver chloride occurs instantly by mixing of aqueous solution of aqueous solution of silver nitrate and sodium chloride. On the other hand, some reactions are very slow. For example, rusting of iron in the presence of air and moisture. Also, there are reactions like inversion of sugarcane and hydrolysis of starch which proceed with a moderate speed. Can you think of some more examples for each category? Now in this examples, what we have said is that first we talked about precipitation of silver chloride. Now this occurs very fast, as in it occurs very instantly. The minute you mix aqueous solution of silver nitrate and sodium chloride, you precipitate out silver chloride. Okay. Then on the other hand, we have seen rusting of iron, that takes a very slow time. So over there the rate of reaction of what? Rusting is very slow because it takes a longer time for the reaction to occur of air and moisture. Only then the coating of that rust is formed. So you must be knowing that the speed of an automobile is expressed in terms of change in position or distance covered by it in a certain period of time. So when we are talking about speed, we say it is the distance traveled, distance into time we say, correct? So in that case, what we are considering, that if I am moving from say point A to point B, so we calculate the distance, how much distance have I moved in how much time, correct? So these are the two things that we find. So similar way, the speed of a reaction or rate of a reaction can be defined as the change in concentration of a reactant or product in unit time. So similar way, when we are talking about the rate of a reaction, we talk in terms of the concentration of the reactant or the product with reference to time. To be more specific, it is to be expressed in the terms of the rate of decrease in concentration of any one of the reactants or the rate of increase in concentration of any one of the products. Okay, say we have A giving us B. So what is happening here? This was okay, let's take a simple example of ice. Okay, say now this A is water and this B, the product that is going to be formed, is my ice. So what will happen if this water has to go to ice? So what will happen here? This quantity of water will decrease, right? The layer of ice will start forming and the liquid, that is the water, will uh, reduce in quantity. If we look at B, then if as this is getting reduced, the quantity of ice will increase. More and more ice will be forming. So this is what we are saying, the rate of decrease in the reactant. Okay, so here the level of water is decreasing, either this or the rate in increase of the product, that is as the level of water is decreasing, the amount of ice is increasing. Okay, so now let's consider a hypothetical reaction assuming that the volume of the system remains constant. So there is no change in volume. So R giving P. So for 1 mole of the reactant, R produces 1 mole of product P. So here stoichiometry is 1. So directly 1 mole of R is giving us 1 mole of product P. If R1 and P1 are the concentrations of R and P respectively at time T1, and R2 and P2 are the concentrations at time T2 then. So initial T1 is initial and T2 will become a final time. So delta T, that is change in time, will be T2 minus T1. Then change in reactants will be R2 minus R1, and change in product, that is delta P, will be equal to P2 minus P1. So the square brackets here, this you see, these are denoted by square brackets. So these here express the molar concentration, or we can say just the concentration. To denote the concentration, we use square brackets. Now let's talk first in terms of rate of the disappearance of reactant, as in the reactant is getting fully disappeared to finally form the product. So that can be given as decrease in concentration of R, volume of the concentration of what the reactant is decreasing, divided by time taken with reference to time. So that can be written as minus delta R upon delta T. Now why is this minus? Because what is happening to the concentration? It is reducing. Therefore we take up a negative sign. Now rate of appearance of P. So that is increase in concentration of P. So in this case what we will get, the time taken will be equal to R plus delta P upon delta T, correct? So here we get this. Now since R is a negative quantity, as the concentration of reactants is decreasing, it is multiplied with -1 to make the rate of reaction a positive quantity. So now here what we saw, that we were getting a negative quantity. Now the rate cannot be negative. So what we do, we multiply it with another negative quantity, that is -1. So the rate of reaction becomes a positive quantity. So the the equations which are given now, these two equations, the rate of disappearance and appearance, these two are known as the average rate of a reaction, and it is given by R subscript AB. So average rate depends upon the change in concentration of reactants or products and the time taken for that change to occur. So it only depends on two things, that is the how much the concentration of reactants or products is changing, and also the time that is taken for this change to occur. Now the units of this rate of reaction. So from equation 3.1 and 3.2, it is clear that units of rate are concentration time inverse. Okay, because we have in the numerator we had the concentration, and here denominator we had time. So if I have to take this on top, it will become concentration and time inverse. Okay, so if the concentration is in mole liter inverse and the time is in seconds, then the units will be mole liter inverse second inverse, because the time goes in inverse because we are taking it into the numerator. However, when we talk about concentration of gases, we express it in terms of partial pressures. So in that case, the rate equation will be in atmospheres second inverse. Now if we see here, we have average rates of hydrolysis of butyl chloride. So we have butyl chloride here. So we have the time taken T1 and T2, and then we have the R average that is removed. So what is happening here? The concentration is reducing. Okay, in both the cases concentration is reducing. So if the concentration is reducing, what do we see? That the rate of average rate also reduces. So it can be seen that the average rate falls from 1.90 into 10 raised to 4 mole liter inverse second inverse to 0.4 into 10 raised to minus 4 mole liter inverse second inverse. However, average rate cannot be used to predict the rate of a reaction at a particular instant, as it would be constant for the time interval for which it is calculated. So now what they are saying, if you have to calculate the average rate, okay, here we have got a series of rates. Now if we want to calculate the average rate, we cannot use this in that case, because if you look somewhere, if we took two middle points, what we can see is that somewhere it might remain constant as well. So in that case, to express the rate of a particular moment of time, we determine the instantaneous rate. So that is obtained when we consider the average rate at the smallest time interval, say dt, that is when delta t approaches 0. So when the time difference is almost 0, hence mathematically for an infinitesimally small delta dt, instantaneous rate is given by. So here we can write for r average equals to minus delta r upon delta t will be equal to delta p upon delta t. Now as delta t approaches 0, we can write, or r instantaneous can be equal to minus dr, because we are looking at a very small change, so we write dr and dt equals to dp upon dt. Now it can be determined graphically by drawing a tangent on time t and either of the curves for concentration of r and p versus time and calculating its slope. So here for this we can draw a tangent. So if I place a scale here, I can draw maybe a tangent like this, and one can be like this. So somewhere here, if we use like a proper scale to draw the two tangents, we will get somewhere here. So at this point, that is at this around 600 seconds. So what we can do is that finding the slope, we can find the r instantaneous. So for r instantaneous at 600, we can calculate given the two concentrations and the time. So we get 5.12 into 10 raised to minus 5 mole liter inverse second inverse. So similar way for different times we can calculate the r instantaneous or the instantaneous rate. So now if we consider another reaction of Hg plus Cl2 giving us HgCl2, where stoichiometric coefficient of reactants and products are same. So here what you see that the stoichiometry is just 1, everywhere it is 1. So in such cases the rate of a reaction will be this minus delta Hg, because these two are going to get reduced. So we'll write minus delta Hg upon delta T equals to minus delta Cl2 upon delta T, giving us plus delta HCl2 upon delta T. That is rate of disappearance of any of the reactants is same as the rate of appearance of the products, because as this is disappearing, this is appearing. So but in the following reactions, if 2 moles of HI decompose to produce 1 mole each of H2 and I2. Now here see the stoichiometry is changing. Here stoichiometry is 2. So this 2 is in 10 getting divided in 2. So we are having 1 plus 1 mole, which is giving us this 2 moles of HI. Now for such cases what we do is that we have to divide the reactant that is there, which has a stoichiometry of 2, we have to divide it by 2. Therefore the rate of reaction here will be equal to rate of reaction equals to minus half, or you can directly write delta HI upon 2 delta T. So that equals to delta H2 upon delta T equals to delta I2 upon delta T. So similarly for all such reactions where the stoichiometry is not same, we have to do the same. So you have to divide the stoichiometry by the given delta T. So here also see everywhere wherever there is a stoichiometry, we have divided that value. So for gaseous reactions at constant temperature, concentration is directly proportional to their partial pressures of a species, and hence rate can be also expressed as a rate of change in partial pressure of reactant or the product. In terms of gases, we talk directly in terms of their partial pressure. So whatever partial pressure change is occurring, that is considered equal to the rate of the reaction that occurs. Now let's talk about the factors influencing rate of a reaction. So rate of a reaction depends on experimental conditions such as the concentration of reactants, how much concentration are we taking into consideration, the temperature and even the catalyst. First, the dependence of rate on concentration. So the rate of a chemical reaction at a given temperature may depend on the concentration of one or more reactants and products. The representation of rate of reaction in terms of concentration of reactants is known as rate law. It is also called as the rate equation or rate expression. So when we are talking about the rate of a chemical reaction, say for any given temperature, we say that it may depend on the concentration of either one of the reactants or whatever reactants that are present in the reaction. So then we can say that the representation of rate of a reaction in terms of concentration, it is known as the rate law, or it is also called as the rate equation or rate expression. Second, the rate expression and the rate constant. So in the table 3.1, we saw that the rate of reaction was decreasing as the passage of time, as the concentration of the reactants was decreasing. So conversely, if the rate generally increases, what does it mean? That the concentration of the reactants is also increasing. So the rate of the reaction, it directly depends upon the concentration of reactants. Now say let's consider a general reactions where we have AA plus BB giving us CC plus DD. So here the small a, b, c and d, they define the stoichiometric coefficients of reactants and products. So the rate of expression for this reaction is given by rate equals to, rate is directly proportional to a raised to x and b raised to y. So x and y can be any stoichiometric coefficient, and it is not necessary that they have to be equal to this a, b, c, d which are given here. So this can be written as, now once removing the proportionality sign, we can add a proportionality constant. So rate will be equal to k, a, concentration of a raised to x and concentration of b raised to y. So this can be written as minus dr upon dt equals to k, concentration of a raised to x, concentration of b raised to y. So this form of equation, it is known as the differential rate equation. So when we write it in this form, dr upon dt, it is called as the differential rate equation. Here k is the proportionality constant and it is also known as the rate constant. So the equation like 3.4, which relates the rate of reaction to concentration of reactants, it is called the rate law or the rate expression. So this becomes our rate law or rate expression. This two, both of this 3.4. So this can be called as this rate law or rate expression. Thus the rate law is the expression in which reaction rate is given in terms of molar concentration of reactants, with each term raised to some power, which may or may not be the same as the stoichiometric coefficient of the reacting species in a balanced chemical equation. So what we are saying in this term, if you see this x and y, what we said is that it should not be equal to the stoichiometry that is given. So it can be different in that case. For example, now if we look at this 2NO plus O2 and giving us 2NO2, we can measure the rate of the reaction as a function of initial concentration of either of them, keeping the concentration of one reactant constant and changing the concentration of other reactants, or by changing the concentration of both reactants. So following results can be obtained. In this case, what is happening? First is initial we have NO and O2 is kept same. So both the concentrations are same. Now here next NO is doubled and O2 is kept same. So what is happening? Here initially the rate was very low. Now the rate has increased, or it has, we can say, maybe doubled. So in this case, when we keep the initial concentration same and we double the initial concentration of O2, then also there is a change in the initial rate. But on doubling both NO and O2, the rate is the highest. So it is obvious that after looking at the results, that when the concentration of NO is doubled and that of O2 is kept constant, see here, then the initial rate increases by a factor of 4. So by a factor of 4, this is increasing from 0.096 to 0.38 mole liter inverse second inverse. So this indicates that the rate depends upon the square concentration of NO. So if you double this, this will also double. So when the concentration of NO is kept constant and concentration of O2 is doubled. So here this is constant, this is doubled. So in that case the rate gets doubled, indicating that the rate depends on the concentration of O2 to the first power. Hence we can write the rate equation for this reaction as rate equals to K NO the whole square and O2, because we saw that on doubling this also doubles, so by that too by a factor of 4, so that is you are squaring the concentration. So the differential form of this rate expression is given as minus dr upon dt equals to K NO2 NO raised to 2 and O2 concentration. Now we observe that for this reaction in the rate equation derived from the experimental data, the exponents of the concentration terms are the same as their stoichiometric coefficients in the balanced chemical equation. But in some examples like this, CHCl3 plus Cl2 giving us CCl4 plus HCl. Here if you see, the stoichiometry is not matching with that of the balanced reaction equation. So rate law for any reaction can be predicted by merely looking at the balanced chemical equation, that is theoretically must be determined experimentally. Okay. So that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.